Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 2.5, Zeros of Polynomials. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. 2.5 Zeros of Polynomials refers to the zeros or solutions or roots to a polynomial equation. So if you are asked to solve for a polynomial equation equal to 0, for example, one way to solve the equation would be to factor. So if you are asked to factor x cubed minus 5x squared plus 2x plus 8, what do you need to get started? Well, the rational root theorem is a theorem that provides us a subset of the real numbers of x values that are possible rational roots of a polynomial. It works by creating fractions of all the constant term factors, in this case the factors of 8, divided by the leading coefficient terms factors, in this case the factors of 1. And I'm going to refer to the rational root theorem as RTT. From this subset of real numbers, we can then test each of the possible rational roots to see if one is actually a rational root. Then we can divide and get the rest of the factors. Well, if we have one rational root, what that means is, if we know, let's write it this way, if we know that x equal to a is a root of the equation, or a solution, of f of x equal to 0, then we know that f evaluated when x is substituted with a equal to 0 is true. Furthermore, we know that a comma 0 is an x-intercept of the graph of f. That is, of course, if a is contained in the real number system. If a is a complex number, then we wouldn't be able to plot the complex number on the real plane with x and y. And so any complex root would not be an x-intercept because we could not plot that complex number on the real number line. Okay, so let's take a look at an example to see how this rational root theorem provides us with this subset of the real numbers that are possible rational roots. Let's take a look. Let's list the possible rational roots of x cubed minus 5x squared plus 2x plus 8 equal to 0 using the rational root theorem. Well, the possible rational roots are going to be the factors of the constant term 8 divided by the factors of the leading coefficient 1. So let's just write the factors of 8. They are 1 times 8 and 2 times 4. So we have 1, 2, 4, and 8 for the factors of 8. And the factors of 1 are simply 1. So we're going to make every combination of the constant factor divided by the factors of the leading coefficient. And of course we could have plus or minus all of these possibilities. So we could have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, and plus or minus 8 over 1. Now you might ask the question, why are the constant factors in the numerator? Let's just take a quick look at a polynomial equation, a quadratic. X squared minus 5x plus 6 equal to 0. Well, in fact, let's make it a little bit different. Let's start off with an expanded form, 2x plus 1 times x minus 3 equal to 0. Let's expand this, where we would get 2x squared minus 6x plus x is minus 5x, and then minus 3 equal to 0. If we use the zero product property, which says that if two things multiply together to give 0, either one factor or the other factor must be 0, then the zero product property tells us that 2x plus 1 equals 0, or x minus 3 equals 0. If that's the case, x equals negative 1/2, or x equals 3. We see that the possible rational roots are of the form where the 1 and the 3 are factors from the constant, and the 2 and the 1 are factors for the leading coefficient. So going back to the rational root theorem, it says that we create fractions of all of the constant term factors divided by the leading coefficient factors. Okay, so here we have our constant term is 8. Its factors are 1, 2, 4, and 8. The leading coefficient is 1. It only has one factor. So let's go back to the current problem. So our possible rational roots, there are in fact 8 different possibilities, plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. Now recall on the previous slide, we said that if x equal to a is a root, if it's actually a root, then when we substitute the root into the equation becomes true. So if any of these 8 possible roots, and they are rational roots because they're made up as ratios, if any of these 8 possible rational roots are actually roots of the polynomial equation, then when we substitute that x value, or that possible root value, into the equation becomes true. So what we need to do is to test each of these values until we get one x value that makes the equation true. The easiest value to test is always going to be x equal to 1. So if we test and substitute in, we get 1 cubed minus 5 times 1 squared plus 2 times 1 plus 8. And that value is equal to, I'm going to add up the positive numbers. 2 plus 8 is 10, plus 1 is 11, minus 5 is 6. So that's equal to 6, which is not true, so this is false. And therefore, we have that this is not a root. Okay, well, we can try another value. Let's test x equals negative 1. Our goal is just to find one x value that is actually a root out of this list of possible rational roots. So if I substitute negative 1 in cube, I get negative 1. Negative 1 squared is 1 times negative 5 is minus 5. Plus 2 times negative 1 is minus 2, and then plus 8. And I see negative 1 minus 5 minus 2 is negative 8 plus 8 is 0, which is true. And so what we found is that x equal to negative 1 is in fact a root. So let's record that x equals negative 1 is a root. And if x equals negative 1 is a root, then by taking that over to the other side, we see that x plus 1 is a factor. We take it to the other side because that would actually say x plus 1 is equal to 0, and working backwards from the zero product property, our factor set equal to 0 became a factor of the original polynomial. So now we know that x plus 1 is a factor. Going back to the remainder theorem and the factor theorem of 2.2, we know that once we have a factor, we have a remainder of 0. Well, the remainder, if you recall, of f of x divided by x minus k was equal to, let me not put equals, that's right, is given by f of k. So in this case, our k value is negative 1. When we sub negative 1 into the function, we got 0. So that 0 is saying that the remainder is 0. And if the remainder is 0, when remainder equals 0, we have a factor. So now what we know is that x plus 1 divides evenly into the polynomial. If we take a cubic polynomial and divide it by a linear polynomial, we will get a quadratic. And from the quadratic, we could continue to factor if the discriminant is a perfect square, or we could use the quadratic formula to solve for the remaining roots. So let's continue to determine all of the roots of the polynomial. So at this point, I'm going to let f of x be defined to be x cubed, I think it was minus 5x squared, plus 2x plus 8. And I'm going to divide f of x by x plus 1 So another thing that I could write is to say that f of x is equal to some linear, well, our linear factor x plus 1 times some quadratic polynomial. This is quadratic because quadratic times linear is x to the 1 times x to the 2 will give me the x cubed that we had here. I'm going to use synthetic division. So if we use synthetic division to divide, I put my -1, which is my actual root, and then I put all of the coefficients 1, -5, 2, and 8 along here. And then I bring down my 1, multiply -1 times 1 is -1, add straight down because I've already introduced a sign change from my factor. -5 minus 1 is -6, multiply, +6, add straight down, 8, multiply, -8, add straight down, and the last term, no matter what its value, is the remainder. But we should have a remainder of 0 because we saw that f of -1 was equal to 0. That's the remainder by the remainder theorem. So what we know now is that our cubic function f of x is equal to the linear function x plus 1 times the quadratic function 1x squared minus 6x plus 8. And with a little bit of luck, we can just factor that using trial and error or other techniques that we've learned in the past. And we have x plus 1 multiplies by x minus 2 times x minus 4. And the question, if we just finish it off, says to determine all of the roots of the polynomial. So now we are substituting f of x with 0. If we substitute f of x with 0, we are looking for the x-intercepts of the function. And then by the zero product property, we get that x plus 1 equals 0, or x minus 2 equals 0, or x minus 4 equals 0, and therefore x equals -1 or 2 or 4. Well, let's just look at the graph of this cubic polynomial to confirm that we have these three x-intercepts. By the way, what is the y-intercept of this polynomial? In fact, let's draw this graph by hand just to practice making a sign chart. We'll do that on the next page. So we know that to make the sign chart, we start off by drawing the x-axis, and we label it with the x-axis, and we list all of the factors or the roots of the factors. So -1, 2, 4. And I'm going to use a faint line, actually I'm going to use this yellow line as a boundary. I'm not plotting my y-axis yet because the y-axis is another vertical line passing when x is 0, and I don't want to create another region here. The root of the polynomial that gave me x equal to -1 is x plus 1. And the multiplicity or exponent on that factor was just 1. The next root of 2 came from a factor x minus 2, again to the 1. And the factor x minus 4 gave us the root of x equal to 4. We can do our sign chart. Hopefully you were thinking graphically when you're doing the sign charts. I'm going to fill it in very quickly. You may want to pause it, try it, and check with my answer. Negative, positive, 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 negative, negative, positive, positive, negative, 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 positive. This times this times this is called f of x. When we multiply all of the factors' signs in the first region or interval, we get negative, then positive, then negative, and then positive. We have seen examples where these signs may or may not alternate. It depends on the exponents or the multiplicities, the number of times each root occurs. The number of times each root occurs, or exponent here, tells you whether the graph will go smoothly through, turn around, or flatten before continuing through, just like the parent power functions. Okay, so now we can do some shading. I will do some light shading in, well, let's take yellow again. If y is negative, y lies below the graph, the x-axis, so the graph will not lie above the x-axis. In the second region, y lies above and therefore not below the x-axis. In the third region, y lies below because it is negative and therefore does not lie above the x-axis. And in the fourth region, we shade below. I'm going to use this sign chart now to make my grid, so I'm taking my numerical approach with pluses and minus signs, meaning positive and negative numbers, and I'm turning the numerical into a graphical by introducing the y-axis. So I'm actually just going to erase this to make room and make it less messy. And my y-axis now goes when x is 0. And of course, labeling it helps to distinguish it from the other boundary lines that you've used. We also want to plot our y-intercept, which, if you notice, when x is 0, we get y is 8. That's a good thing because when x is 0, y has to be positive. You don't have to plot these very carefully by marking spaces and numbers. The end behavior of this polynomial will be the same as y equals x cubed. So I'm just going to write here in red the end behavior model. Model is just another term for function or example. So the end behavior model is y equals positive x cubed, which has end behavior, well, looks like that. So our end behavior will be f of x's end behavior will look like this, something going on in the middle, and like this. In other words, we say the limit as x approaches negative infinity of f of x equals negative infinity, because as we go to the left, or as x goes to the left, y goes down, and as x goes to positive infinity, y goes to positive infinity. So the limit as x approaches positive infinity of f of x equals positive infinity. And because we have multiplicity 1 for all of the roots, we're going to go smoothly through. It is unlikely that the one point that we have plotted between x equals negative 1 and 2 happens to be the local maximum or turning point, and it seems likely that the maximum is going to occur after the y-intercept. So our graph will do something like this. This is as accurate as we can be in precalculus until we get to calculus. Something like that, and let's look at the graph program to see how we did. Y equals x cubed minus 5x squared plus 2x plus 8. I'd say not bad. So we can put that graph in the lecture notes just so we can see two different perspectives. Maybe I'll make this a little bit bigger. Okay. And add these to the lecture notes. Okay, so we got our three roots, negative 1, 2, and 4 for x. All right, go ahead, pause the video, determine all roots of this. The one thing I will say by way of introduction is that you can refer to this as f of x. You can let f of x equal the polynomial x cubed minus 2x squared minus 5x plus 10. And once we have realized we have replaced y with 0, this means that we are setting y equal to 0 so that we are getting the x-intercepts of the polynomial. Okay, pause the video, try repeating this process from exercise 1 in exercise 2. Okay, so the possible rational roots are going to be plus or minus the factors of the constant divided by the factors of the leading coefficient. The factors of the constant are 1, 2, 5, and 10, and the factors of the leading coefficient 1 is just 1. So we are going to get plus or minus 1 over 1, 2 over 1, 5 over 1, or 10 over 1. Obviously, if the coefficient is 2 or 3 or 5 or 6 or something else, we will have more possibilities, and then we would have to repeat dividing each of the factors of 10 by the other factors of the leading coefficient. So we get 1, 2, 5, 10. You know, I'm going to put this one here and this one in green because I don't use green so much. And then I'm going to put over 1 over 1 over 1 over 1. So you can see where this 1 came from. Now what we need to do is test. Again, the easiest x value to test is x equals positive 1. And so we want to work out what f of 1 is. We get 1 minus 2 minus 5 plus 10, which, well, I've got too much positive going on here, so this is not equal to 0. So this means that x equal to 1 is not a root. So we pick another value, maybe x equal to negative 1. The reason I'm choosing it is because we don't have to change the coefficients except for the plus or minus, based on whether we have negative 1 to an odd or negative 1 to an even exponent. So here f of negative 1 equals negative 1 minus 2 plus 5 plus 10, and we see that this is not equal to 0 either. Okay, so x equal to negative 1 is not a root. So I'm going to try x equal to 2. I'd really not like to put 10 in here and cube it if I can avoid it. So x equal to 2 gives me f of 2, which is going to be 2 cubed is 8, minus 2 times 2 squared is going to be minus 2 times 4 is minus 8, then minus 5 times 2 is 10, and then plus 10. And that, in fact, is 0. So we have identified a root. So x equal to 2 is a root, and x minus 2 is a factor of f of x. Okay, so now let's go ahead and find the other factor. If x minus 2 is a linear factor, then it would have to multiply by a quadratic to give me the cubic. So we perform long or synthetic division. I'm going to do synthetic division. So x minus 2 is a factor of f of x. Therefore, f of x equals x minus 2 times some quadratic. So this is degree 1. This is degree 3. And this must be degree 2. So positive 2 for my synthetic division outside of the coefficients, which were 1, negative 2, negative 5, positive 10. And performing synthetic division, 2 times 1 is 2, negative 2 plus 2 is 0, 2 times 0 is 0, negative 5 plus 0 is negative 5, 2 times negative 5 is negative 10, 10 plus negative 10 is 0, and this last number always represents the remainder. Well, from the remainder theorem, recall that the remainder is f of 2, and that's equal to 0 because we have a factor. The 0 that we're getting here from the synthetic division and the 0 that we get here are the same. However, we may also interpret this. This also means that 2, 0 is an x-intercept of the graph y equals f of x. So there's lots of different interpretations of this 0. It just is the remainder. It's a remainder of 0, which means we have a factor, or it's the y-coordinate when we have the x-intercept. So there's lots of different ways to interpret the 0. The more ways we understand, the better understanding and long-term retention we have. All right, let's take a look then. If f of x is x minus 2 times the quadratic is 1x squared plus 0x minus 5, and we get f of x equals x minus 2 times x squared minus 5. Well, we can factor this as a difference of squares very easily. The only problem is we don't have 5 as a perfect square, but it's not really a problem because we get x minus the square root of 5 times x plus the square root of 5. The square root of 5 and negative square root of 5 are not rational. So this is an interesting example. These are not rational numbers. So the possible rational roots from the rational root theorem say that if the function f of x has rational roots of the form integer over integer, then they will be one of these 8 possibilities. What this is telling us is that there is one rational root and two irrational roots. That means that any of the other possible rational roots will not substitute in and make f of x equal to 0. So the only three roots, because we have a cubic polynomial, the maximum number of roots we can have is 3, and the three roots are 2, positive root 5, or negative root 5. So if I were to set y equal to 0, we would get x equals 2, or positive root 5, or negative root 5. Again, we should be able to make a sign chart, draw the graph, and confirm. These should all represent x-intercepts on the graph. So 2, 0, or root 5, 0, or negative root 5, 0. For purposes of graphing, we should be able to approximate the square root of 5. We know that 5 lies between two perfect squares of 4 and 9, and therefore the square root of 5 lies between the square roots of 4 and 9, which are 2 and 3. So therefore the square root of 5 is approximately 2 point something. Okay, let's draw a sign chart, make a sign chart, and draw the graph, just so we can be clear on how all of the algebra and numerical work connects graphically. So we have f of x is equal to x minus 2 times x minus the square root of 5 times x plus the square root of 5. Sign chart, here's the x-axis, here's x equal to 2. The square root of 5 is 2 point something, and if I put negative 2 over here, then the square root of negative square root 5, oh, I didn't want to undo all of that, oh well, 2 square root of 5, negative 2, and a little more to the left would be negative square root 5. Okay, this is my x-axis, so I'm going to label it, and then I'm going to use a faint line for my boundaries. I like this yellow one. The factor that gave me the root negative square root 5 is x plus square root 5. The factor that gave me x equal to 2 is x minus 2, and the factor that gave me square root of 5 is x minus square root of 5. Now you should be making sure you can do the sign chart on your own. I'm going to fill it in very quickly. You can take test points in each of the 4 regions or intervals, or you can think graphically about each of these linear functions and where the graph would lie above or below the x-axis. This times this times this is equal to f of x, and in the first region f of x is negative, so y will not lie above the x-axis, or the graph will not lie above. In the next region, y is positive, so the graph will not lie below the x-axis. In the third region, y is negative, so the graph will not lie above. And lastly, y is positive, so the graph will not lie below. Now I'm just going to tidy up my sign chart so I can turn it into a 2-dimensional graph by introducing the y-axis and information about y. So far we only have information about x. So halfway between these two x-intercepts of negative root 5 and positive root 5, I have x equal to 0. Label the y-axis, especially important when you have other vertical lines being drawn. And go back to the function in expanded form and recognize that when x is 0, y is equal to 10. Again, that's good news because we have a positive region for y when x is 0. The graph has multiplicity 1, or roots that go through one time, and so we have a very similar graph. Let's just check the end behavior. If I were to expand this polynomial, well, it was expanded. It was x cubed plus lower ordered terms, so the end behavior for x cubed looks like this, and our end behavior will look like this, with something going on in the middle, and like this at the end. And that's all confirmed by the sign chart. Again, it's unlikely that this point is going to be the maximum, since how likely is it you can pick one thing out of an infinite number of possibilities? So everything about this graph shape is similar to exercise 1, but what is different is that we only had one rational root and we had two non-rational or irrational roots. Okay, You can take a look in the graphing calculator to confirm, but I'm pretty sure this is the right graph. Let's take a look at the next example. Let's solve this by hand. So here what we want to do is recognize that we have a cubic polynomial. We could take everything to one side. And let's give it a function name of f of x. So what we're really saying is we want a cubic polynomial to lie higher or on the x-axis. So I'm going to refer to the x-axis as y equal to 0 in red. So it's hard to know exactly what this graph is going to look like, but if we just came up with a suggestion, we have the y-axis here, we have the x-axis in red, and we have the leading term is 3x cubed, which means that we have the same end behavior as x cubed. So our blue f of x graph may look something like this. Now it's hard to know if maybe this these two x-intercepts will converge here and turn around like this. But let's just imagine that we've got three distinct x-intercepts. If those values are called a, b, and c, you should have no trouble solving for where the blue graph lies higher or on the x-axis. So if this is the case, our solution would be where the graph in blue lies on or above the x-axis would be the highlighted portions of the blue graph. Similarly, we are saying we want the x-axis to lie on or below the blue graph, which would be here or here. And so our solution in terms of the numbers or the letters a, b, and c would be x is contained from a to b inclusive, union from c to infinity. So all that remains in this question is to find the numbers a, b, and c. I'd like you to think about how you can put that together, and I'll have this completed in the lecture notes. You can compare it there. Moving on to the next theorem. It's the irrational theorem that says if a polynomial with rational coefficients, so your polynomial has coefficients ax to the 4 plus bx cubed plus cx squared plus dx plus m, for example. The coefficients are the a, b, c, d, and the constant m. So if those coefficients are rational, meaning that they are integer over integer, but if we have an irrational root of the form a plus the square root of b, then the irrational conjugate must also be a root. So we're going to take a look at this next activity or exercise using the TI-Inspire calculator. Determine an equation of a polynomial with rational coefficients, so these are all quotients of integers, with the smallest possible degree, whose roots include these numbers. Well, these are irrational numbers, so let's let one of the roots be called 3 minus the square root of 2. The irrational root theorem says that automatically a second root must be the irrational conjugate, where we change the sign of the irrational term. So 3 plus root 2, square root of 2, must also be a root of the equation. Furthermore, we are given that the square root of 5, which is 0 plus the square root of 5, is a root, and therefore another root must be, change that to a 4, another root must be 0 minus the square root of 5, or negative square root of 5. So we should probably make this spread out a little bit more. Let's see. Okay, so if we have this is a root, let's actually call them x values. So this is an x. And so if we take this to the other side, we have a factor of x minus 3 minus the square root of 2. This factor is going to be x minus 3 plus the square root of 2, because this is coming to the other side to set equal to 0, so that from the zero product property, these factors can be multiplied together. This is an x value, so we take this root to the other side and we get the factor is x minus the square root of 5, And again, this is an x value. We take this root to the other side, so we get a factor of x plus the square root of 5. It's possible that there could be other factors and therefore other roots, but if we want the smallest degree possible, we do not want to introduce any other factors. So therefore, f of x could be each of these 4 factors multiplied together. So x minus 3 minus the square root of 2 times x minus 3 plus square root 2 times, I'm just going to use round brackets here, x minus root 5 times x plus root 5. We should have no problem expanding this. We just saw it in one of the previous examples that this is x squared minus 5. You should be able to expand this by hand, and I'll leave you to do it as an exercise, but we are going to use it with the calculator. So if we expand on the calculator, we can go ahead and type, I'm going to make this a little bit smaller so I can see behind it. And let's take a look at what the expression is. We've got x minus 3 minus the square root of 2. So the square root we can find here, times x minus, in brackets, 3 plus the square root of 2, times x minus the square root of 5, times x plus the square root of 5. And we can see that not much happens here, so we may need to force the calculator to do a little bit more for us. Let's go to the catalog feature above the division, and we are going to go into the catalog to E for expand, or F and cursor up to expand. We are going to expand this expression, and when we do that, we see x to the 4 minus 6x cubed plus 2x squared plus 30x minus 35. This is a polynomial of degree 4, and what we want to confirm is, are the coefficients rational numbers? In fact, 1, negative 6, positive 2, positive 30, and negative 35 are not only rational, but because they all have denominators of 1, they are also integers. Let's take a look at this graphically and confirm what the values of the x-intercepts are. So if we look at y equals x to the 4 minus 6x cubed plus 2x squared plus 30x minus 35, we see that we have indeed 4 x-intercepts, and let's just confirm that that's all there are. Okay, we can't see any more. And if we take a look at the different x values by tracing, because we have irrational numbers, it's hard to tell what the numbers are. So what we're going to do is draw 4 vertical lines, and the vertical lines, I'm going to type them in as x equals the square root of 5, x equals negative the square root of 5, and instead of actually drawing these 2 vertical lines separately, I'm going to combine them as x squared equals 5. And we see that those 2 vertical lines are the same as the expression x squared equals 5. It's hard to see the second one. Maybe if I zoom in here a little bit. It's very difficult to see this green one. Let me change it to blue, and we can see the blue line coming in here. Okay, we also have 2 other vertical lines. X equals, what did we have for our roots? X equals 3 minus root 2 and 3 plus root 2. So we have 3 minus the square root of 2, and x equals 3 plus the square root of 2. And we can see, sure enough, that those x values intersect at the x-intercepts. So we got the right x-intercepts, and we had enough factors to make the minimum degree such that we have rational coefficients. The last example is very similar. We have a repeat of this question. And where did it go? The last example is the complex root theorem says that if a polynomial has real coefficients and the complex root of the form a plus bi is given, then we automatically must have the complex conjugate a minus bi to be a root. The reason is when we multiply these 2 roots together, these 2 complex conjugates, we get a real number. So if we repeat the same process for a polynomial equation with real as opposed to rational coefficients in the last example of smallest degree with the following roots, let's see what other roots we will need to include to guarantee real coefficients. So we know that x will equal root 1 of 5, which is already a real number, so there's no partner or irrational, or rather complex conjugate needed. Another x value for the root is 3i plus the square root of 2. I'm going to write that so we have the real coefficient, or the real part, first. And automatically, therefore, we know that the complex conjugate of square root of 2 minus 3i is required by the complex root theorem. And we know that x equals root 4 is negative I, which is 0 minus I, and therefore another x value, another root of 0 plus I, or simply I, must be involved. Putting those all together, we get factors. This factor is x minus 5. This factor is x minus 2 plus 3i, root 2 plus 3i. This factor is x minus root 2 minus 3i. This factor is x plus I, because minus negative I. And this factor is x minus I, if we take it across. And therefore the polynomial will be of degree 5, which will be all of these blue factors multiplied together. If I take these two things and multiply them together, I get x squared plus 1. So I may just write that in place of these two individual factors. So x minus 5 times x squared plus 1 times the two longer factors. Now I can write x and then distribute the negative sign through. X minus root 2 minus 3i times x minus root 2 plus 3i. And from here, let's see what the calculator says when we expand. Hopefully all of the coefficients become real numbers and do not involve I. So in the calculator, we are going to expand x minus 5 times x. I'm still going to use the plus I and the minus I rather than x squared plus 1. Actually, what I'm going to do first is verify that x minus I times x plus I is indeed x squared plus 1. And it is. So now I'm going to continue expanding, and I'm going to multiply by x minus 5 as well as x minus square root of 2 minus 3i, as well as times x minus the square root of 2 plus 3i. And when we look at the expansion, we get coefficients of 1, negative 2 root 2, both of those are real. Negative 5 is real. 2 square root 2 is real. It is not rational, but it is irrational, which is real. 12, same with the negative 2 root 2. 12 is real, rational, integer, whole number, and natural. Negative 2 root 2 for the x squared is real. Negative 60 is real. 10 root 2 is real. 11 is real. And negative 55 is real. So we have accomplished our goal of coming up with a polynomial with real coefficients of the smallest degree without introducing any additional factors that are unnecessary to make this real. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.